Welcome to the Coatings Talk live chat podcast. I'm Jim Kunkel, and I greatly appreciate everyone joining this live chat podcast session. As we're getting started, I'd like to cover the session disclaimer. This live chat podcast and the Coatings Talk series does not represent the opinions or strategies of Akzo Nobel International Paint. Additionally, I make every effort to provide accurate and up-to-date information from the global protective coatings and corrosion industries. Now, despite this care and attention, it's reasonably possible that the content and live conversations within this session may have content that is incomplete and or inaccurate. I am recording this session audio for rebroadcasting as an audio podcast on the Coatings Talk channel. Before I set up today's topic, I'd like to cover how you can participate in this live session. It's real easy. All you have to do is use the raise your hand icon in the chat menu. Also, please feel free to hit any emoji to let me know how you're feeling about this live chat session. The topic is going to be Cathodic Protection 101, just the basics. Cathodic protection is a technique used to control the corrosion of a metal surface by making it the cathode of an electrochemical cell. A simple method of protection connects the metal to be protected to a more easily corroded sacrificial metal to act as an anode. The sacrificial metal then corrodes instead of the protected metal. Let's get into this topic. Cathodic protection systems protect a wide range of metallic structures in various environments. Common applications are steel pipelines that transport water and or oil and fuel. You have storage tanks and other assets from home water heaters, steel pier piles, ship and boat hulls, offshore oil platforms, and onshore oil well casings, offshore wind farm foundations, and metal reinforcement bars in concrete buildings and structures. Another common application is in galvanized steel, in which the sacrificial coating of zinc on steel parts protect them from rust. Cathodic protection can in some cases prevent stress corrosion cracking, which is the growth of a crack formation in a corrosive environment. It can lead to unexpected and sudden failure of normally ductile metal alloys subjected to a tensile strength, especially at elevated temperatures. Let's talk about the history of cathodic protection. Cathodic protection was first described by Sir Humphry Davy in a series of papers presented to the Royal Society in London in 1824. The first application was to the HMS Samarang in 1824. Sacrificial anodes made from iron were attached to the copper sheath of the hull below the waterline, dramatically reducing the corrosion rate of the copper. However, a side effect of cathodic protection was the increase in marine growth. Usually copper, when corroding, releases copper ions, which have an anti-fouling effect. Since excess marine growth affected the performance of the ship, the Royal Navy decided that it was better to allow the copper to corrode and have the benefit of reduced marine growth. So cathodic protection was not used further. Davy was assisted in his experiments by his pupil Michael Faraday, who continued his research after Davy's death. In 1834, Faraday discovered the quantitative connection between corrosion weight loss and electrical current, and thus laid the foundation for the future application of cathodic protection. Then in 1890, Thomas Edison experimented with impressed current cathodic protection on ships, but was unsuccessful due to the lack of a suitable current source and anode materials. It would be 100 years after Davy's experiment before cathodic protection was used widely on oil pipelines in the United States successfully, and a cathodic protection was applied to steel gas pipelines beginning in 1928 with wider implementation during the 1930s. Now let's talk about galvanic impressed current cathodic protection, or ICCP, and hybrid systems. Starting with galvanic. In the application of passive cathodic protection, a galvanic anode, a piece of a more electrochemically active metal, which means more negative electrode potential, is attached to the metal surface where it is exposed to an electrolyte. An electrolyte is any substance that undergoes ionization when dissolved in water or ionizing solvents. This covers almost all soluble acids, bases, and salts. At times, gases like hydrogen chloride can also act in a similar way to electrolytes, given there is a low pressure or high temperature. Electrolytes play a vital role in the corrosion process since their presence triggers a reaction between two dissimilar metals. Galvanic anodes are selected because they have a more active voltage than the metal of the target structure, which is typically steel. Now, concrete has a pH of around 13. In this environment, the steel reinforcement has a passive protective layer that remains largely stable. Galvanic systems are constant potential systems that aim to restore the concrete's natural protective environment by providing a high initial current to restore passivity. It then reverts to a lower sacrificial current while harmful negative chloride ions might migrate away from the steel and towards the positive anode. The anodes remain reactive through their lifetime, 10 to 20 years typically, increasing current when the resistivity decreases due to corrosion hazards such as rainfall, temperature increases, or flooding. The reactive nature of these anodes makes them an efficient choice. Unlike impressed current, cathodic protection systems, ICCP, still constant polarization is not the goal, rather the restoration of the environment. Polarization of the target structure is caused by the electron flow from the anode to the cathode. So the two metals must have a good electrically conductive contact. The driving force for the cathodic protection current is the difference in electrode potential between the anode and the cathode. During the initial phase of high current, the potential of the steel surface is polarized. It's pushed. More negative protecting the steel. When hydroxide ion generation at the steel surface and ionic migration restore the concrete environment. Over time, the galvanic anode continues to corrode, consuming the anode material until it eventually must be replaced. Galvanic or sacrificial anodes are made in various shapes and sizes using alloys of zinc, magnesium, and aluminum. ASTM International publishes standards on composition and manufacturing of galvanic anodes. In order for the galvanic cathode protection to work, the anode must possess a lower, that is more negative, electrode potential than that of the cathode, which is the target structure to be protected. Impressed current cathodic protection, or as it's known as ICCP. Simple impressed current cathodic protection systems. A source of DC electric current is used to help drive the protective electrochemical reaction. In some cases, impressed current cathodic protection systems are used. These consist of anodes connected to a DC power source, often a transformer rectifier connected to AC power. In the absence of an AC supply, alternative power sources may be used, such as solar panels, wind power, or gas-powered thermoelectric generators. Anodes for ICCP systems are available in a variety of shapes and sizes. Common anodes are tubular and solid rod shapes or continuous ribbons of various materials. These include high silicon, cast iron, graphite, mixed metal oxide, platinum, and niobium coated wire and other materials. For pipelines, anodes are arranged in ground beds, either distributed or in a deep vertical hole, depending on several design and field condition factors, including current distribution requirements. Cathodic protection transformer rectifier units are often custom manufactured and equipped with a variety of features, including remote monitoring and control, integral current interrupters, and various types of electrical enclosures. The output DC negative terminal is connected to the structure to be protected by the cathodic protection system. The rectifier output DC positive cable is connected to the anodes. The AC power cable is connected to the rectifier input terminals. The output of the ICCP system should be optimized to provide enough current to provide protection to the target structure. Some cathodic protection transformer rectifier units are designed with taps on the transformer, windings, and jumper terminals to select the voltage output of the ICCP system. Cathodic protection transformer rectifier units for water tanks and used in other applications are made with a solid-state circuit to automatically adjust the operating voltage to maintain the optimum current output or structure to electrolyte potential. Analog or digital meters are often installed to show the operating voltages, DC and sometimes AC, and current output. For shore structures and other large complex target structures, ICCP systems are often designed with multiple independent zones of anodes with separate cathodic protection transformer rectifier circuits. Let's talk about hybrid systems. Hybrid systems have been incorporating the condition monitoring and high restorative current flow of ICCP systems with the reactive, lower cost, and easier to maintain galvanic anodes. This system is made up of wired galvanic anodes in arrays typically 400 millimeters or 16 inches apart, which are often initially powered for a short period to restore the concrete and to power ionic migration. The power supply is then taken away and the anodes are simply attached to the steel as a galvanic system. More powered phases can be administered if needed. Like galvanic systems, corrosion rate monitoring from polarization tests and half-cell potential mapping can be used to measure corrosion polarization. It is not the goal. Polarization, is not the goal for the life of the system. Now let's talk about some real-world applications of cathodic protection. Pipelines. Hazardous pipelines are routinely protected by coatings and supplemented with cathodic protection. An impressed current cathodic protection system, ICCP, for a pipeline consists of a DC power source, often an AC power transformer rectifier, an anode or array of anodes buried in the ground, which is the anode ground bed. The DC power source would typically have a DC output of up to 50 amperes and 50 volts, but this depends on several factors such as the size of the pipeline and coating quality. The positive DC output terminal would be connected via cables to the anode array, while another cable would connect the negative terminal of the rectifier to the pipeline, preferably through junction boxes to allow measurements to be taken. Anodes can be installed in ground bed consisting of vertical hole backfilled with conductive coke, which is a material that improves the performance and the life of the anodes, or laid in a pre-prepared trench surrounded by conductive coke and backfilled. The choice of ground bed type and size depends on the application, the location, and the soil resistivity. The DC cathode protection current is then adjusted to the optimum level after conducting various tests, including measurements to pipe to soil potentials or electrode potential. It is sometimes more economically viable to protect a pipeline using galvanic sacrificial anodes. This is often the case on smaller diameter pipelines of limited length. Galvanic anodes rely on the galvanic series potentials of the metals to drive cathodic protection current from the anode to the structure being protected. Water pipelines of various pipe materials are also provided with cathodic protection, where owners determine the cost is reasonable for the expected pipeline service life extension attributed to the application of cathodic protection. Let's talk about ship hulls. Cathodic protection on ships is often implemented by galvanic anodes attached to the hull and ICCP for larger vessels. Since ships are regularly removed from the water for inspections and maintenance, it's a simple task to replace the galvanic anodes. Galvanic anodes are generally shaped to reduce the drag in the water and fitted flush to the hull to also try to minimize drag. Smaller vessels with non-metallic hulls, such as yachts, are equipped with galvanic anodes to protect areas such as outboard motors. As with all galvanic cathodic protection, this application relies on a solid electrical connection between the anode and the item to be protected. For ICCP on ships, the anodes are usually constructed of a relatively inert material such as a platinized titanium. A DC power supply is provided within the ship and the anodes mounted on the outside of the hull. The anode cables are introduced into the ship via a compression seal fitting and routed to the DC power source. The negative cable from the power supply is simply attached to the hull to complete the circuit. Ship ICCP anodes are flush mounted, minimizing the effects of drag on the ship, and located a minimum 5 feet below the light load line in an area to avoid mechanical damage. The current density required for protection is a function of the velocity and considered when selecting the current capacity and location of the anode placement on the hull. Some ships may require specialist treatment. For example, aluminum hulls with steel fixtures will create an electrochemical cell where the aluminum hull can act as a galvanic anode and corrosion is enhanced. In some cases like this, aluminum or zinc galvanic anodes can be used to offset the potential difference between the aluminum hull and the steel fixtures. If the steel fixtures are large, several galvanic anodes may be required, or even a small ICCP system. Marine structures. Marine cathodic protection covers many areas: jetties, harbors, offshore structures. The variety of different types of structures lead to a variety of systems to provide protection. Galvanic anodes are favored, but ICCP can also often be used. Because of the wide variety of structure geometry, composition, architecture, specialized firms are often required to engineer structure-specific cathodic protection systems. Sometimes marine structures require retroactive modification to be effectively protected. Now let's talk about steel rebar and concrete. The application to concrete reinforcement is slightly different in that the anodes and the reference electrodes are usually embedded in the concrete at the time of construction, when the concrete is being poured. The usual technique for concrete buildings, bridges, and similar structures is to use ICCP, but there are systems available that use the principle of galvanic cathodic protection as well. Although in the UK at least, the use of galvanic anodes for atmospherically exposed reinforced concrete structures is still considered experimental. For ICCP, the principle is the same as any other ICCP system. However, in a typical atmospherically exposed concrete structure such as a bridge, there will be many more anodes distributed through the structure as opposed to an array of anodes as to use on a pipeline. This makes for a more complicated system, and usually an automatically controlled DC power source is used, possibly with an option for remote monitoring and operation. For buried or submerged structures, the treatment is similar to that of any other buried or submerged structure. Galvanic systems offer an advantage of being easier to retrofit and do not need any control systems, where ICCP typically does. For pipelines constructed from pre-stressed concrete cylinder pipe, the techniques used for cathodic protection are generally as for steel pipelines, except that the applied potential must be limited to prevent damage to the pre-stressing wire. The steel wire in a PCCP pipeline is stressed to the point that any corrosion of the wire can result in failure. An additional problem is that any excessive hydrogen ions as a result of an excessively negative potential can cause hydrogen embrittlement of the wire, also resulting in a failure. The failure of too many wires will result in a catastrophic failure of the pre-stressed concrete cylinder pipe. To implement ICCP, therefore, it requires very careful control to ensure satisfactory protection. A simpler option is to use galvanic anodes, which are self-limiting and need no control. Now, for internal cathodic protection, vessels, pipelines, and tanks, and that also includes ballast tanks, which are typically used to store or transport cargoes, liquids, commodity. They can also be protected from corrosion on their internal surfaces by the use of cathodic protection. ICCP and galvanic systems can be used, and a common application of internal cathodic protection is water storage tanks and power plant shell and tube heat exchangers. Galvanized steel. Galvanizing generally refers to hot dip galvanizing, which is a way of coating steel with a layer of metallic zinc or tin. Lead is sometimes used and added to the molten zinc bath. And also other metals have been studied. Galvanized coatings are quite durable in most environments because they combine the barrier properties of a coating with some of the benefits of cathodic protection. If the zinc coating is scratched or otherwise locally damaged and the steel is exposed, the surrounding area of zinc coating typically will create a galvanic cell with the exposed steel and protect it from corrosion. This is a form of localized cathodic protection. The zinc acts as a sacrificial anode. Galvanizing while using the electrochemical principle of cathodic protection is not really cathodic but sacrificial protection. In the case of galvanizing, only areas very close to the zinc are protected, hence a larger area bare steel would only be protected around the edges. Okay, I'm going to, at this point, kind of end this just the basics conversation. And then eventually what I'll look to do is break out into additional corrosion protection topics on future live chat podcasts. And also, too, on the Coatings Talk, when I do the live episode recordings to produce a video episode, I'm going to focus on corrosion topics, cathodic protection, and other topics from the corrosion prevention and corrosion topic side as well, because they do very well when it comes to people consuming that content. So I really greatly appreciate this opportunity to present this topic with you. And what I want to do in this pause is, if you do have anything that you would like to add, experiences, anything you would like to add to this topic we talked about, or maybe you have something you want to talk about related to this topic, you can just go ahead and raise your hand, and then what I can do is open up your mic, bring you up on stage, and you can join in the conversation. But if you don't, that's okay. All right. Well, I'm going to go ahead and move on. Now, let me talk to you how about you can really support this content. If you are interested as a professional to get involved in doing content like I do, both video, audio, what I would recommend is a platform that I use, which is called StreamYard. StreamYard is an online resource for content creators where you can do live streaming. You can also record your audio and your video. It has a lot of unique capabilities to it. And I do have a referral program. And with the referral program, what I usually tell people who are thinking about getting into content creation and using a platform like StreamYard, sign up for the monthly. The referral that I have will give you $10 off your second month. So it's $25 a month for the platform. Try for a couple months, do some content, and if you get value out of it, then what I would do is recommend you to look at getting an annual subscription. And instead of paying $25 a month, you'll be paying roughly about $20 a month. And it's really worth it, what the features and benefits the program offers you. So I will post a referral link to this session. And then after this session's done, I'll take the recording and upload the audio to my Coatings Talk channel, and also rebroadcast or repost that out on social media. Okay, so on next Wednesday's Coating Talk live chat podcast, the topic will be concrete surface preparation. I'm going to be covering the ICRI, the CSP 310.2R 2013. So we're going to be talking about the ICRI CSPs. And the next session will continue this new combination of a live chat and then recording it to produce an audio podcast, and just like we completed right now. So I hope that you'll participate and join in the conversation on ICR CSP 310.2R-2013. This session will be on Wednesday. What would that be? Wednesday, October 3rd or 4th? I apologize. I didn't look at the thing. And starting at 8 p.m. Eastern Daylight Time. Okay, have a great evening, day, or morning, no matter where you're listening from. Thank you so much.